My favorite number is 16. It's a great number for a lot of reasons. For instance, it's a square number, making it useful in many different circumstances. It's also a power of 2, which makes it a number that computers work well with. But the real reason 16 is my favorite number is something more subtle. Like I said, it's a square number, 4 squared specifically. It's also a power of 2, but not just any power of 2, it's 2 to the 4th power. This means that 2 to the 4 equals 4 to the 2. As soon as I realized this, my mind filled with questions. The foremost question was, are there any other numbers like this? To be more exact, are there any other pairs of x and y where x to the power of y equals y to the power of x? If so, what are they? And if not, why? Now, maybe you already know the answer to this, but pretend you're me for a second. You just came across this piece of math that you've never heard anyone talk about before. You've watched plenty of math explainers before, yet none have talked about this particular thing. You're sure someone has thought about this before, but you don't know who. You've got 3 options: ignore it, look it up, or figure it out. I chose to figure it out. In fact, I decided I would figure it out all on my own. I wasn't going to look up anything until I'd either figured it out or determined I couldn't figure it out. This is my journey of how I found my first ever mathematical proof. The first thing I thought to do was to simply check and see if there were any other pairs of numbers that fulfilled this condition. I tried combinations like 2 and 3, 3 and 6, 3 and 9, 4 and 16, etc., and none of them worked. I soon decided that the best way to do this would be brute force. So I wrote a quick Python script to check all the pairs under 100,000. It found nothing. I even started it going to 1,000,000, but it was taking way too long to get anywhere. At this point, it was pretty clear that there weren't any more integer solutions, or at least not any for a very long time. But I still hadn't proven anything. I had shown that it was unlikely, but I didn't really know why, beyond intuition. So I began to think about it a little more analytically. I pretty quickly figured out that for 2 pairs of numbers to possibly work, one had to be a power of the other. The reason for this is quite simple if you think about it. If 2 numbers are equal, then they obviously share the same prime factors. This axiom can be taken in the other direction. In order for 2 numbers to be equal, they must share all their prime factors. When you raise a number to an integer power, you don't add any new prime factors. You only change the quantity of the factors. So this quickly rules out solutions like 2 and 3. They share no prime factors. Additionally, the 2 numbers must have the same basic ratio of prime factors. To understand what I mean by that, let's take the example of 6 and 12. The prime factors of 6 are 2 and 3. 12 also has 2 and 3 as prime factors, but it has an extra 2 as well. If we raise 6 to any power, there will always be the same number of 2's as 3's. That is to say, the ratio of 2's to 3's will always be 1 to 1. However, if we raise 12 to some power, it will always have a 2 to 1 ratio of 2's and 3's. There will always be twice as many 2's as 3's in a power of 12. Therefore, there's no way that a power of 6 and a power of 12 could ever be equal. So, I determined that one of the 2 numbers had to be a power of the other. This is about the point where I got stuck for a while. Actually, I hadn't even quite gotten to this point. I was right on the edge of it, but I got stuck on this idea of grouping factors together. As you'll soon see, that idea was actually critical to the solution and proof, but I was missing the other piece. I was beginning to get worried that I had tackled a problem that was far beyond my ability. It seemed so simple, and I felt like the solution was right there, but I just couldn't find it. Before long, I let the idea go and forgot about it. Then I saw Grant's video on 3 Blue 1 Brown about the Summer of Math exposition. That video and contest gave me the motivation to tackle this problem again. So I did. I gave it another go, and this fresh wave of motivation actually allowed me to solve it in under an hour. The solution didn't come instantly, of course. What I decided to do was to try to find a different way to write the problem. Instead of writing it as 2 to the 4 equals 4 to the 2, I wrote it as 2 to the 2 times 2 equals 2 times 2 to the 2. I then further expanded each side out into its factors like this. By grouping the factors like this, we can see several things. First, there are overall the same number of factors on both sides. Because of this, they are equal. However, grouping the numbers like this gives us some insight. On the left, we have one large group made up of 4 2's. We can also split this into 2 groups of 2 2's like this. This corresponds to the exponent being 2 times 2. On the right side, we also have two groups of two 2's, but we put the parentheses in a different spot. This is because each group of 2 is being treated as a unit. There are 2 of these units because the exponent is 2. So, how does this help us find our proof? Well, let's see what happens if instead of 2's we use 3's. Remember, we already proved that the two numbers must be powers of each other, so we can safely assume that they will be in a form like this. Quick side note, this isn't the only form that could work, but we'll get back to that later. So, let's try another value of x. This is what happens if we try x equals 3. Now we can see a little bit better what's going on. On the left side we have 9 3's, and on the right we have 6 3's. We can once again see the grouping of factors. We're starting to see a bit of a pattern here. For 3, the number of factors on the left is 3 squared, and on the right is 3 times 2. If we continue the pattern for 4, 5, 6, etc., we see that the pattern still holds. Therefore, we can deduce that for any integer n, the left side will have n squared factors, and the right side will have 2n factors. Like we established earlier, for both sides of the equation to be equal, they need the same number of factors. Now we have a way to express the number of factors algebraically. All we need to do is make an equation and solve it. When we solve this equation, we get 0 and 2 as the solutions. We can ignore 0 because 0 times 0 always equals 0, so that just leaves us with 2, which is exactly what we were looking for. This equation is proof that 2 is the only x that can work in the equation form x to the x times x equals x times x to the x. Therefore, we just proved that 2, 4 is the only integer solution to the x to the y equals y to the x, where x does not equal y. Or did we? You see, we only looked at one equation form. Let's look at it again. We can rewrite x times x as x squared. But what about x cubed, or x to the fourth? Well, let's try the same process again. Let's try the x cubed form and see what happens when we set x to 2. When we expand this, we get different numbers of factors, so the equation isn't true. But look at the number of factors on each side. On the left, we have 8 factors, or 2 cubed. On the right, we have 6 factors, or 2 times 3. This is the same pattern as we saw before, just with 3 instead of 2. So, we can make an equation and solve again. And if we plug the square root of 3 back into our equation form, then we find that it works out perfectly. It may not be immediately obvious how this relates to this, but let's see what happens when we solve the equation with 4 in it instead of 3. We get the cube root of 4. We can, of course, check that it works. But now let's compare all 3 of these solutions we found so far. Since it's pretty clear at this point that the pattern continues, let's ignore the right side and just look at the left side. Look at the main number, that is the x and x to the y equals y to the x, in each expression. Notice the pattern now? If we put the root number out in front of the radicals, it's even clearer. The main number always looks like this. Now we know what the x and y and x to the y equals y to the x must be. X is the n minus 1 root of n, and y is the n minus 1 root of n to the n. Because of the definition of a root, an nth root raised to the n equals whatever was under the radical. Since we have the n minus 1 root and we are raising it to the nth power, we will always end up with a number under the radical, in this case n, with one radical left over. So we can write y as n times the n minus 1 root of n. This gives us our final form for our equation. The amazing thing is that this doesn't just work for integer values of n. If you plot the graph of one of the sides of this equation with n on the x-axis and this expression on the y-axis, you can see that any value of n works in this equation. Interestingly, the graph looks almost linear, getting even more so the further away you get from 0. The larger n gets, the closer this expression gets to n. As n approaches 0, the value shoots off to infinity since the negative first root of 0 is undefined. And right there, at n equals 2, we have our number that started this whole thing, 16. So what's the point of doing all this? I could have easily gone online, looked this up, and found all this and probably more in minutes. In fact, there are plenty of other great videos on this topic. But I wanted to figure it out myself. I could have just put x to the y equals y to the x in a graphing calculator, but that doesn't really show you what's going on. By first analyzing the problem and figuring out what its constraints are, that y had to be a power of x, breaking down the problem to its basics, and continuing the pattern, I was able to take the concrete examples of what worked and didn't work and form a more abstract algebra equation. Then once I found why this particular example worked, I extended the pattern even further and found another solution. By generalizing again, I was able to find the equation for every solution to this problem, not just one. And further, by finding this equation form, I was able to definitively prove what I was hoping to all along, that 2 and 4 are the only integer solutions.